Alright, this is the notes for section 4.4, composing reflections over parallel lines. If you haven't done so already, please pause the video at this time and read the section before going on with these notes. Okay. The first thing I want to look at is the language of composition. So we really have to basically we're kind of defining what a composition is here. But if you think about the activity that we did in class, we took a triangle ABC and we reflected it over line M to get its image. Okay, that image being A prime, B prime, C prime. And then we took the image, that new figure that we got, and reflected it over N to get a second image, or the image of the image. Okay. This, if I take that idea and starting with this right here, since I know triangle A prime, B prime, C prime is equal to the reflection over M of ABC, I can substitute the reflection over M of triangle ABC into this statement. So this is saying exactly the same as this. So really what we're saying is the reflection over N of the reflection over M of triangle ABC is triangle A double prime, B double prime, and C double prime, or the second image of that figure. Okay. Well, when we do this, when we take one transformation is followed by another transformation, we say that the transformations have been composed. Therefore, the reflection over N and the reflection over M have been composed, and the result is what we call a composite of transformations. Okay. Well, let's define what a composite is. When we say a composite, the composite of a first transformation S and a second transformation T can be written like this. Okay. T, and then this symbol, and then S. Okay. And what that is it's a transformation, okay, that maps every point to the point T following S of P. Now what does that mean? Well, basically it means that we're going to take a point, we're going to perform whatever transformation S is on it. So we're going to move it in some way using the transformation S. And then we're going to take the result from that and move it in some way using the transformation T. Okay? So in terms of how we write that, and we'll get into more of what those composites look like, but in terms of how we write that, it's written like this, and it's read T following S. The reason why it's read that way is we're actually going to perform the S transformation first and the T transformation second. Okay? This symbol is just called the composition. Okay? And if you think about how this writing it like this, we have another way of writing that using the composition symbol, and that is the reflection over N following the reflection over M of triangle ABC is triangle A double prime, B double prime, C double prime. Okay? These two statements mean the exact same thing. Now, what's important for us to understand is that when we apply these transformations, they're applied first is written on the right. So the first transformation that I'm going to do is not over N. The first transformation that I'm going to do is the transformation over M. And then I'll do the transformation over N. Okay, throughout this chapter we're going to look at several compositions, all of which are built off of the reflection that we did in 4.1 and 4.2. And the first composition that we're going to look at is a translation. It's also called a slide. A translation or a slide is the composite of two reflections over parallel lines. Okay? Therefore, if A is parallel to B, then we would say that the reflection over A following the reflection over B is equal to T, where T is a translation. Okay, so a translation is reflection over two parallel lines. Now, some properties of translations. Because a translation is two reflections, those things that we talked about being preserved in reflections, mainly angle measure, betweenness, collinearity, and distance, so that ABCD piece, all of those things are preserved in translations because I'm still doing reflections. So if they're preserved in reflections and I do more than one reflection, they must be preserved when I do that as well. So translations would have to preserve all four of those things as well. When we describe a translation, okay, we need two things to describe it. We need to know a distance and a magnitude. Distance, which is its magnitude, and then we also need to know a direction. Okay, so every translation will have a distance, which we call its magnitude, and a direction. Okay, when we talk about the magnitude of a translation, we're talking about the distance a figure is translated or slid or moved on our sheet of paper. It is found by measuring the distance from any pre-image point to any image point. Okay? And when we talk about the direction of a translation, it can be given by a ray from any pre-image point through any image point. Okay? Okay, let's take a look at example number 1 then. It says find the distance and the direction of the translation that maps PQRS onto its image P double prime, Q double prime, R double prime, S double prime. So to do that, what I'm going to do is I'm going to get my ruler, and first thing I'm going to do is I'm going to measure the distance. And it doesn't matter what points you use as long as you pick a pre-image point and an image point. So I've got my ruler set up to deal with P and P double prime. Okay, and if I measure that distance on my ruler, and now mine might be different than yours because I've scaled it up here on the screen a little bit, but using this ruler and using the distance that I have on the screen, I've got a distance of about 5.7 centimeters. So the distance, which I can write really as a length from P to P double prime. So I can say P double prime is equal to 5.7 centimeters. That would represent the distance. Now, to find the direction, well, the direction is using a ray. So I could say, in terms of writing that, I would write it as P double prime, that ray. Okay, and I'm going to actually draw in that ray as well. So to draw in that ray, I'm going to start at point P, and you can do this using your ruler. And I'm going to go through P prime, not just to it, but through it. And that ray would represent the direction of that translation as well. Okay, so let's not forget what a translation is. A translation, remember, is two reflections over lines that are parallel to each other. Okay, I have an example of a translation down here involving two reflections, and we're going to talk about what we know about that. Okay, we also know that a translation, being defined by those two reflections over parallel lines, we also know that it's going to be defined by a distance and a direction of that translation. Okay, well, the two reflection theorem for translation tells how we can kind of coordinate those two ideas of doing two reflections over parallel lines, and what that tells us about the magnitude or the distance of that translation, and also what it tells us about the direction of that translation. Okay, so here's what it says. It says if two lines M and L are parallel to each other, so any two lines that are parallel to each other, and we do a translation such that we do the reflection over M following the reflection over L. So the reflection over L is my first reflection. The reflection over M is my second reflection. Okay? It has a magnitude of 2 times the distance between L and M. Okay? So in other words, the distance that it's going to move will always be twice the distance between the two lines. So whatever the distance between the two lines is, we're going to double it to get the magnitude of that translation. Okay? And then the direction will always be from L perpendicular to M. In other words, from the first line towards the second line, perpendicular to those two lines. Okay? So down here I have an example of a translation involving two reflections. My lines are J and K, and I'm doing the reflection over K following the reflection over J of triangle EFG, and I get the image, which is E double prime, F double prime, G double prime. So I'm going from here to here. This is just work to help me get there. Okay, so let's look at how that works. So I'm going to take this thing and I'm going to first reflect it over J. So if I take EFG and reflect it over line J, I'm going to get this figure right here. Okay? And then I'm going to take that figure and reflect it over K to get my final image right here. Okay? Now, the two reflections theorem for translation tells us this, that if the distance between these two lines, okay, which we can measure with HL, is 1.05 inches, then the distance that the figure moves, and we can measure that from G to G double prime, or from F to F double prime, or from E to E double prime, that distance is going to be double this distance, which is 2.10 inches. Okay? It also tells us, the last part here, that the direction of that translation will be a ray going in the direction from the first line of reflection, in this case J, towards the second line of reflection, in this case K. If I were to take, say, F, I can draw a ray from F through F double prime. And that ray will give me the direction of that translation. So we could write that as the ray F double prime. So let's take a look at number 2 here. It says let A be a line described by the equation x equals 5. So I've graphed that here. Let B be the line described by x equals 1. I've graphed that in both of these. And then it says describe the translation of the reflection over A following the reflection over B, which I have over here, and compare it to the translation of the reflection over B following the reflection over A. Okay? So you'll notice in this one over here, I take M, I first reflect it over A, and then I take that point, M prime, and reflect it over B to get A double prime, or excuse me, M double prime. Okay? And over here, I'm going to start by reflecting over B, and then taking that image point and reflecting it over A to get my final image. Okay? Now, it said to describe those translations. Well, in this one here, all the points, doesn't matter where the point is, and I just picked a point M, but every point will move to the left 8 units. Okay? Now, I know it's going to be 8 units no matter what because of my two reflections theorem for translation. The distance between these two lines is 4, therefore the distance that it moves is 8 units. The direction that it moves, remember, is in a ray from the first line towards the second line. So the direction is going to be perpendicular to these two lines, which is horizontally in that direction. Okay? And then if I look at the reflection over A following the reflection over B, it also moves 8 units, but it's going to move to the left because I'm going from the first line towards the second line, so I should be going in this direction horizontally. Okay? Now, then it says compare the translations. Well, the translations have the same distance, however their directions would be opposites of each other. Okay, let's look at example 3 here. It says copy this diagram, which I've included on your notes. Use it to show that the distance between the pre-image R and its translation image R double prime is twice the distance between the two lines. Well, if I measure the distance from R to R double prime using my ruler, I find that that distance is equal to 2.8 centimeters. And if I measure the distance between these two lines from here to there, I find that it's 1.4 centimeters. Okay? Therefore, since R double prime is equal to 1.4, the distance between the two lines, times 2, which is also equal to 2.8, therefore we have a true statement there.